your rockets. Next class, you have to bring your rockets in made, ready to test. With your haikus. With the haikus. That's your ticket to come and test. But you bring them in next time on that. So, we're going to talk about some machines here. Last time we talked about mechanical advantage. Now you need to know where that is because you will need those formulas for the exercise when we get to that. But levers. Remember, we talked about inclined planes. Just a ramp, simplest form of machine. The other, basically the other type of machine, because they're all either inclined planes, are levers or levers. By the way, both pronunciations are correct. Lever or lever. Now, a lever has two parts. It has a fulcrum and the lever. The fulcrum, the lever is the bar. The fulcrum is the pivot. And how we classify them and how much mechanical advantage depends on that relationship between the load, the effort, and the fulcrum. In other words, we normally look at what's in the middle. What's in the middle? First class or type 1 levers. The fulcrum is in the middle. The load is on one end, and the effort is on the other. Now, this is unique among the levers. One, it is the only lever that changes direction. Notice I push down, thing goes up. The only one that changes direction. It's also the only one that really can give you equal force out. In other words, a first-class lever can be said, if you put the fulcrum in the middle, whatever force I put in is equal to the force I get out. So it can be set that way on that. But it's the only type of lever. And our classic Class 1 lever, the teeter-totter. Teeter-totter is a Class 1 lever. Also a jack. If you have the type of jack that you put the handle in, you click down. It's like one click and it goes up a little bit. That is a first-class lever that you're doing. Notice you're pushing down, your car is going up. First-class lever on that. Anyone need more time? All right. So the other two types of levers. Second class levers or type 2 levers. In this case, the load is in the middle, the effort is in one end, and the fulcrum is at the other. So the load is in the middle. Type 2 levers, load is in the middle, are classic. The wheelbarrow. You know, you have a wheel in the front, that's the fulcrum. You pull up on the handle at the end and all the dirt and stuff is in the middle. Same class lever. Because let's think about how much you put in the wheelbarrow. Could you lift a bag full of that much dirt? Probably not. You have a big wheelbarrow, that's a lot of dirt. A lot of cement. You fill it up with cement, you know, it's a lot of rock. You would not be able to lift it on your own. But by using the wheelbarrow, you're able to lift much more. But notice, the effort and the load are going to go in the same direction. Both going to go in the same direction. And you get more force out than you put in. The third class lever, or type 3 lever, the effort is in the middle. And you have the load at one end and the fulcrum at the other. Again, both go up. Both go in the same direction. But notice, you put in more effort, you get out less force. Right? But you do this larger effort for a short distance, you get this smaller effort, smaller load for a much longer distance. And your limbs, this is how your limbs work. All your limbs are third class levers, are a series of third class levers. Every joint, every time you see a joint, is a separate third-class lever. So here on my finger, I have 3 third-class levers. My hand is a third-class lever. Forearm, my upper arm, all third-class levers. And it's where it attaches. You know, sometimes we look at it. If you look at your forearm. Where are the muscles that allow your forearm to move? Where are those muscles? Yeah, they're the bicep and tricep are the muscles. Then you might say, well, that looks like a first-class lever, right? It's like, well, I got my muscles here. Here's my fulcrum is in the middle, and then my load's over here. But no, it's not where the muscle is. It's where the muscle attaches. Notice, even though the bicep is up here, notice where it actually pulls on. This bicep muscle pulls on the forearm, so it's where it's attached, and they're always one back. Your wrist muscles are controlled by your forearm. There's muscles in your hand that control your fingers, and so on. But it's where it's attached. This is also determines how strong and things like that, how strong you're going to be. How much mechanical advantage can you develop? And this is just the way you're made. You know, some of you may spend a lot, just years and years at the gym. You're never going to be a power lifter. Why? Just because your body just isn't made that way. Nothing wrong with that. It's just you were made that way. There's other people, you look at them, it's like they don't look to be that, like they could lift all that weight. Well, it's just that where their muscles attached, they can develop more mechanical advantage. Just like, if you sprinters and long distance runners, do they look the same? When you look at Olympic sprinters, you look at long distance runners, are their bodies the same? No. I mean, sprinters, they actually look like weightlifters, don't they? They have big muscles, arm muscles, leg muscles. And then long distance guys are usually really kind of thinner, lankier, have to do where their muscles are, where they attach, their musculature and things like that. It's all about leverage. It's all about where the mechanical advantage. Even look at different primates. Look at chimpanzees. Humans and chimpanzees. Now, the average human, I think, are about 6 feet tall. It's about the average male human. Average chimpanzee is, I think, at 5'4". A full-grown male chimpanzee is about, if it stood up, it's like about 5'4", something like that. Obviously, human beings are bigger. Human chimpanzee, who's stronger? Chimpanzee stronger. Who has more muscle mass? Human. Humans have more muscle mass. We have more muscle mass. And why is the chimpanzee stronger? Because the chimpanzee, where their muscles are attached, they get more mechanical advantage out of what they have. Even though they have less muscle mass, they do that. It makes them stronger. However, does a chimpanzee have as much endurance as a human being? No. In fact, if you look at different animals, human beings have one of the longest endurances there are. Human beings can run a very long time. You have to get in shape and things like that, but much longer than most other animals. But usually we have much more endurance and much more ability to deal with extremes. Well, let's think about what animal is basically in every climate in the world. Humans are the only ones. You might think, well, chimpanzees are stronger, blah, 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 but then again, who's the endangered species? Yeah. All right, so let's look at a little video about levers.
Eureka! The story so far. A machine is something that helps you use your energy more effectively. One of the simplest machines is the inclined plane, which allows you to trade increased distance for decreased effort or force. By doubling the distance you move a thing, you can half the force you need to exert. And now, the lever. If you're sitting on a teeter-totter, looking for someone to teeter-totter with, and then a big fat guy comes along, what do? Do you want to risk it? Now, there's an easy way you could have avoided that. Two easy ways, in fact. You could have either have asked the fat guy to move nearer and nearer to the middle of the teeter-totter until you balanced. Or else, you could have made a little adjustment to the teeter-totter before he sat down on it. And then, you would also have balance. Both methods really boil down to the same thing. You see that support the teeter-totter is resting on? Well, scientists have a fancy word for that. They call it a fulcrum. which is simply Latin for a support or pivot. Anyway, whether the fat guy moves himself closer to the fulcrum, or whether you move him closer to the fulcrum by moving the teeter-totter, the result is the same. The distance between him and the fulcrum becomes less than the distance between you and the fulcrum. And that's the secret of successful teeter-tottering with people heavier than yourself. Or for that matter, the secret of the successful balancing of any object with any other heavier object. If you want to balance a 100 Newton weight with another 100 Newton weight, you place them both at an equal distance from the fulcrum. Let's say 2 meters. But if you want to balance a 100 Newton weight with one that's twice as heavy, you move the 200 Newton weight nearer and nearer the fulcrum until it's in just the right place for the 2 weights to balance. Now you know how to lift a 200 Newton weight with a force of only 100 Newtons. It looks as if you're getting something for nothing, doesn't it? But you're not. Don't forget that the 200 Newton weight is nearer to the fulcrum than you are. How much nearer is it, in fact? 1 meter? So the distance between you and the fulcrum is exactly double the distance between the 200 Newton weight and the fulcrum. That means that you have to move your end of the teeter-totter exactly twice as far as the weight moves. You exert a force of 100 newtons through 1 meter in order to lift a weight of 200 newtons through half a meter. What you win on the force, you lose on the distance. Sound familiar? Of course. It's precisely the same principle as that of the inclined plane. When you double the distance, you can halve the force. This is true whether you're using an inclined plane or a teeter-totter. Only we should stop calling it that, because when we use it to make work easier, it's really another sort of simple machine. It's really a lever. Yes, a lever. You use levers all the time, things that give you leverage. After the inclined plane, it's the commonest simple machine in the world. Even cavemen knew about levers. Not to mention old Archimedes in ancient Greece, who was actually the first person to state the principle of the lever. The longer the arm of the lever to which force is applied, the less that force need be. In fact, he got so excited about this one day that he said, "Give me a fulcrum on which to rest, and I will move the earth." That may have been taking things a bit too far, but at least you now know enough to go down and apply Archimedes' principle of the lever to your teeter-totter.
All right, so those are all about levers. A lever, a lever. Now, if you look up the dictionary, it's pronounced both ways. Leads us to pulleys, which actually is another type of lever. Pulleys. Pulleys have 2 types that work together. You have the fixed pulley. It doesn't move. It only changes the direction of motion. It works like a first-class lever that has the fulcrum in the middle. Then whatever input force you have, you get output force. But like the first-class lever, it changes the direction. So if the girl here pulls down, but it pulls up. But how many lines are here? How many lines are supporting this? 1. There's only 1 line supporting it, so she has to pull with all the weight. Only changes direction of the force. The moving pulley changes how much force. And it does just that. It moves up and down with the load, like this. And it works like a second-class lever. And basically every sheave gives you 2 more on your mechanical advantage. The sheave is what we call the little wheel. The little wheel and the pulley. Like this is a single pulley. It's a single sheave pulley. Notice how many lines are supporting here. Think about the Nellie Newton. How many lines are supporting that load? 1, 2. There are 2 lines. It's being supported on both sides. Now I know it's one continuous line, but it acts like it's being supported on 2 sides. which means if this weighed 100 newtons, what would be the tension on each of those lines? 50. So she only has to pull up with 50 newtons less force. But again, like all simple machines, she's going to use less force. She's going to have to pull more, what? More distance. In this case, more rope. In other words, if she wants this to go up 1 meter, she's going to have to pull 2 meters of rope. She pulls with half the force, but she has to pull twice the distance on that. Now the reason we use these pulleys, I mean, why would be that? Why don't we just use this all the time? Why even worry about the fixed pulley? Well, let's think even here. Why would we want to pull down rather than have to pull up? What? Heard it. It's easier. Yeah, it's easier. Biomechanically, in other words, the way our bodies are made, we actually get more mechanical advantage pulling down than pulling up. I mean, it's just the way we're made. Our bodies are made to pull down rather than pull up, which is one of the reasons even just having a single pulley makes it easier, because it's a lot easier to pull down than it is to pull up. In other words, if I wanted just to lift this up, say, to a platform up here, I mean, I could run a line down and just drag it up. Or I can put it in the pulley and pull it up. It's actually, even though the force technically is the same, it is easier to pull this way than to have to pull up this way. But when I have that, it's going to reduce the force. Anybody in time? There's that trade-off here. Trade-off. You have to pull more line and the load does not go up as fast. If you ever watch a really big crane, you know, sometimes these big giant cranes, they might have a block that's the whole thing down here. They may have like 8, 10, 12 sheaves in it. And if it's lifting something, it moves really slow. But you watch the reel that has the cable itself, it's moving really, really fast. It's pulling a lot of cable in really, really fast. But because of all that, it takes it more. Now the compound pulley, we just fix these two together. But it's only the lines touching the moving pulley that determines the mechanical advantage, the change in force. In this case, I have 1, 2 lines, which in theory should give me a 2-to-1 mechanical advantage. Again, this would be a TMA. So TMA with pulleys, I can get from the distance, how much line do I pull, how much does it go up, against that geometric reality. No matter how much force is involved in friction, you know, they're going to move because of the length of the lines and the wheels and all that stuff. But we know it's a 2-to-1 mechanical advantage. If I had a block that had 1, 2, 3 sheaves in it, there, each sheave is going to have 2 lines. So 1, 2, 3, 4, 5, 6. A 6-to-1 mechanical advantage because each sheave touches 2 lines. And if I attached another one just to the moving block, that would be a 7th one. Sometimes you see it attached up here. Notice this one, they attach the moving block at the top. Sometimes they'll attach the moving block on the single line. So you have to look to see how they're making that attachment. But notice this line right there. Is that adding anything to it? No, because this line is really the extension of that last line. All it does is change direction so that this can go up and she can pull down. The pulleys work like this. Any questions on pulleys? Now we are going to do a lab coming up where you're actually going to look at several, even though we're doing inclined plane today, we're going to be looking at some efficiencies later on between pulleys and things like that. Anyone need more time on this?
Story so far. There are only 2 basic machines, the inclined plane and the lever. All other machines are variations of these. A screw is simply a twisted inclined plane. A wheel is simply a circular lever whose fulcrum has become an axle. And now, the pulley. The pail of water that Jack and Jill had to fetch was not on top of the hill at all. It was actually at the bottom of a well. Unfortunately, it was too heavy for either of them to pull out. What they needed was a simple machine to give them a mechanical advantage. No, the inclined plane doesn't help. Nor does the lever. Nor the screw. What other sorts of machine are there? Ah, yes, the wheel. But what's Jill doing with it? She is arranging the wheel so that it will revolve on an axle stuck in that post. Very good. Jill's just rediscovered another sort of simple machine. A wheel that instead of being all of a piece with its axle, can revolve freely around an axle. Since this type of wheel is used mainly for pulling things, it's called a pulley. And Jill can hitch the rope around it and use it to pull. No, Jack can use it to try to pull the pail of water up. That's funny. He needs just as much force to try to pull the pail of water up this way as he did trying to pull it up the other way. I wonder if there's a better way of rigging the pulley. Amazing. How did Jill manage it? Both she and Jack only had one pulley to work with, and yet Jill was able to pull up the pail with half the force that Jack needed. Well, when a pulley is set up like this, it's called a single fixed pulley. All it does is change the direction of your pull, but it doesn't reduce the force you need. But when a pulley is arranged like this, it's called a single movable pulley, and it halves the force you must exert, because the pail of water is now, in effect, being lifted by two ropes instead of one. It's as if two people were lifting the pail, and it looks as if we're getting something for nothing again, doesn't it? But of course we're not. If we compare the distance that Jill raised the pail with the amount of rope she pulled, we see that it's the same old story. What she's gaining on the force, she's losing on the distance. The distance that she pulls the rope is twice the distance that she raises the pail. But the way Jill used the pulley is still twice as effective as the way Jack used it. There are lots of other ways of combining pulleys, and it's simple to figure out the mechanical advantage of each system. All you do is count the number of ropes supporting the weight. This single fixed pulley has one piece of rope supporting a weight of 600 newtons. Input force 600 newtons. Output force 600 newtons. And the mechanical advantage is therefore 1. There isn't any mechanical advantage, in other words. This single movable pulley has two ropes supporting the weight. Input force 300 newtons. Output force 600 newtons. Mechanical advantage 2. Here's a system with 3 supporting ropes. Input force 200 newtons. Output force 600 newtons. Mechanical advantage 3. This one also has a mechanical advantage of 3, and is, in fact, the pulley system that Jill finally rigged up for herself. Although she had to pull the rope 3 meters for every meter that she raised the pail of water, she only needed 200 newtons of force to do it. In a sense, she'd become 3 times as strong as Jack. And now you know why Jack fell down and broke his crown.
All right, so our last thing today, power. Power. Not entirely helpful to list energy, how much energy something uses, because if I want to know how much, I have a light bulb, and I want to know how much energy it's going to use, I need to plan out. Well, it really depends on how long I run it. Obviously, if I run a light bulb for 10 minutes, and I run it for an hour, they're going to use different amounts of energy. But it doesn't help me plan for that energy usage. So we use power. power. And our symbol for power is a capital P. Our unit is the watt, which is a capital W. We named that for James Watt, who perfected, but he perfected the steam engine. It's what allowed the steam engine to be used for all kinds of different applications. Now, a watt is a joule per second, energy per time. Its SI dimensions are a kilogram meter squared per second cubed. These are the SI dimensions of power. And power is the rate at which work is done or energy is used. Remember, we use it for all kinds of energy. In fact, we'll see in heat, when we talk about heat engines, we talk about how much, we don't say how much energy goes into the engine, how much energy goes out. We talk about how many watts of power go in and how many watts go out. This is going to tell you how much energy per time. Per time. In other words, P W over T, but it could be any type of energy per time. Energy per time. How fast we transform. Because even you put on a light bulb, it says 40 watts. Well, what does that mean? Well, it means I'm going to get, when I have this light bulb on, it's going to transform 40 joules of electrical energy to thermal and light every second. It's using 40 joules of energy per second that it's on. Yes, sir. So joules are energy. Joule is our unit of energy. Regardless of what kind of energy we're talking about, energy is energy. A joule. So a joule per second of energy. All right, so you look on the, most electrical equipment will have somewhere on it a little tag that gives the power rating, how much power, how much current it draws, what power it's going to take, things like that, how much it's going to use in that. And that's where they get the kilowatt part of kilowatt hours, how many kilowatts you're looking at. But a kilowatt hour is actually energy, because if I took power, which is energy per time, and I multiply by time, I end up with energy. That's why kilowatt hour is energy. All right. Well, that's it for our notes today, but we're not done with our lecture notes. We're done with this part. We do have a exercise. Everybody done with this? So we have our exercise. It's about inclined planes. And we have a problem. How does the ramp angle affect mechanical advantage? In other words, as I drag a mass up this ramp, how does increasing the angle of this ramp as I drag it up going to affect the mechanical advantage that I receive because I am using my ramp, my inclined plane? All right, so you guys need to make a hypothesis. What do you think? Is it going to increase? As we increase angle, is it going to increase mechanical advantage? Or is it going to decrease mechanical advantage as we increase that size? You guys need to make this chart. Also, someone needs to go get a ramp, which is on top of the cabinet. See back here where it says the butts are gross poster, way up there in the corner? There are little ramps, little boards. You're going to get boards that look like this one. Grab one of those boards. Also, you need to grab a couple of bricks out of the cabinet. So we're going to take about 3 minutes or so, make this table, grab your equipment, then we will get started on that.